Hey guys, and welcome to another repair/explanation video. This one is going to be about the Lenovo ThinkPad USB-C docking station that you can see here. It's not one of the classical docking stations where you put actually your laptop onto. It's a USB-C extender, so to say, so you connect that via USB-C to your laptop, and then it has all the connections on the back. The failure mode of these, as far as I know, is always the same. So at some point in time they just stop working. So when you plug the power into the charger, when you plug the charger in, the light doesn't come on anymore. And when you put your ear real close to the charger, you can hear a clicking sound once every second. And that usually means that your charger is detecting an overcurrent or a short circuit on the output and thus shutting down. So this thing develops a short circuit inside, and I will talk about that. Why that happens later in this video, and also how you can fix that in this case. This video is not really a step-by-step tutorial. It's more or less an informative video that will give you the information that you need to be able to fix this problem. So you need to be confident to do such a repair. I'm not going to explain every little detail here. So it involves soldering and also SMD soldering, not really micro soldering, but it is on SMD level. So if you've never touched a soldering iron in your life before, maybe this repair isn't for you. However, it might still be interesting to watch what happens here and what the error cause actually is. So the important part of this is where you plug the charger in. It's a 20-volt charger with the Lenovo rectangular power jack. And usually it's the 135 watt version. This is what this docking station needs to be able to also charge your laptop over USB-C power delivery. Maximum, I think, 65 or 90 watts even. You can also run this docking station with a 90 or even 65 watt charger, but then it will not charge your laptop. It will just be a docking station, so a port extender. So first thing, of course, you have to do when you want to take this apart is find out where to get in. So you turn it around, and on the back side you see no screws at first, but there are these these rubber feet, and also there is the sticker. And here I marked the location of in total 5 screws, so 4 under each of these bumpers, and 1 is hidden under the label here. When you run over that with your finger, you can feel the little indentation. There is the screw under there. These are all Phillips head, however it's 3 different types, so make sure to remember which screw goes where when you put that thing back together. Once you've undone those screws, you can clip the red bottom part of this out. It will not go out straight away, but it's not clipped in very, very hard, so you can get that out quite easily. And then what you will most likely be greeted with is the logic board. And there will most likely be something like that on it. So a burnt spot that you can easily see. You will also be able to smell it. And this is a pretty bad example. I also had other ones that more or less look like this. So in this case, I have already removed the defective component here, labeled Q1. I'm going to explain what that is in a second. But here you can see that just the component is damaged and gone now, whereas the traces are still intact. In this case, however, you can see the traces are in pretty bad condition. Some components here are missing, and yeah, this big trace is more or less gone. But also this is fixable just in a different way. So if you're lucky, this is what you will end up after you found the area and cleaned it a little bit. And to be able to explain what this area is and what it does, I'll have to go to a small circuit diagram that I drew here. So this area or this circuit is what's called an Inrush current limiter, and it does pretty much what it says. It limits the inrush current that occurs whenever you plug the charger in. This is very important on laptops where you plug in the charger more or less every day, because what happens is the charger has the 20 volts in it, but the device that you are powering with it has some capacitance that is not charged at the beginning, and once you plug the charger into the device, a lot of current will flow in there to charge the capacitors up, and that is what's called inrush current. And this can actually be quite high. It can be in the hundreds or even thousands of amps for a very short moment of time, so a couple of microseconds, maybe a millisecond or something. And this sort of current will over time damage your connector, your DC plug that you plug in the laptop, because that's of course not able to handle such a current, especially when it's still moving and there is arcing and so on. So when you don't have an inrush current limiter, you will over time damage or wear out your connectors. So as I said, in a laptop it's very important to have such an inrush current limiter. In this case, where it's a stationary device that you set up once and then leave untouched for years maybe, in my opinion, an inrush current limiter is not really necessary. However, it's of course good design practice, and this is why Lenovo has done it in this case as well. So now I'm going to explain how this inrush current limiter limits this inrush current. And the main part is this P-channel MOSFET labeled Q1. So it is important that it is a P-channel, and a P-channel MOSFET will allow current to flow from source to drain when the gate voltage is substantially lower as the source voltage. There is a threshold that is usually somewhere in the neighborhood of 5 or 10 volts, but the important part is this gate voltage has to be lower than this source voltage to be able to pass current from the source to the drain. So what happens initially is this whole circuit here is discharged, so there is 0 volts on there, and then you come along and plug in your charger, so suddenly there is 20 volts here. This fuse is more or less always intact in these cases because the charger has a output over power protection, so it will not deliver more power than it's supposed to, so it will usually never break this fuse, but you can of course still measure it just to be sure. So then 20 volts is coming in here, and in the first moment, because there is a capacitor here that is not charged, it will have 0 volts across it, so this point on the gate will also be the same as source. So the first moment you plug the charger in, there's 20 volts here and 20 volts here. And now, because there is a resistive divider, in this case 75K, this voltage will slowly go to 10 volts, so half of the 20 volts. However, because of this capacitor, it will not do it right away. There is a time constant involved there. I did not measure this capacitance. I assume it's in the neighborhood of 1 microfarad, or a little bit bigger, might be 10 microfarads. But this forms a low-pass filter or a time delay circuit. So this gate voltage will decrease from 20 to 10 volts over time and over the course of a couple of, let's say, milliseconds. And when it does, so when this voltage decreases from 20 to 10 volts, at some point this MOSFET will start conducting. However, it will not completely be closed and just conduct all the current. It will first be in the linear region and only allow a certain amount of current to go through. And that amount of current then slowly charges up the capacitors on the output. And at some point this voltage will have decreased to 10 volts. And then this MOSFET is fully turned on, and then it's basically a short circuit. So then it only has a couple of milliohms in here, and from that moment on you can completely ignore this circuit. It will basically be closed, so then the power from the charger can flow straight to the load. But the important part is, when the voltage is coming on here first, it will not go through straight away. It will have to wait a little until this voltage on the gate has decreased and until these capacitors have slowly charged. So this is what the circuit is supposed to do, and it also does that really well. So after I explained the inrush current limiter in principle, here is another picture of the failed device in the USB-C docking station, which the trace is drawn onto it. So what's basically happening is, on top here is where you plug into a charger. So there's your 20 volts coming from. So red is always the 20 volt line, blue is ground. So you have this fuse F1, which again is usually never broken. Here is where Q1, the P MOSFET, would sit, and then the power would continue onwards down here. In yellow you see the gate section. So you have the one capacitor on top, you have the resistance on top, and then you have the other resistor going to the bottom. So these resistors are the voltage divider, together with this capacitor form the time delay circuit that slowly brings the gate voltage down, and at some point the MOSFET switches on, current can flow from source to drain, and basically then your circuit is on. And these four capacitors are the ones that are shown in the circuit diagram. And now, before we go to the fix, of course I have to talk about the issue that this unit initially has, and that is concerning these 22 microfarad capacitors. So there is always a certain rule of thumb when you want to have a component with a certain specification. So when you want to have a capacitor with a certain voltage rating and a certain capacitance. In this case, it's 22 microfarad capacitance, and the voltage needs to be at least 25 volts because that's the next standard voltage that is sufficient for 20 volt line. So we have in this circuit that I'm going to show you, or that I showed you before, we have 4 capacitors. These are these 4, I will call them big guys for now because they are the biggest components in this circuit. So these are 4 capacitors, 22 microfarad, 25 volts each. And these are still pretty small considering that they are 22 microfarad. This is, I think, the 1206 or 1210 SMD package, which is, in my opinion and in my experience, way too small for a 22 microfarad 25 volt capacitor. So apparently there are manufacturers out there that can produce these capacitors in such a small size, but that has a drawback. And the drawback is that they have to be manufactured very precisely with very little tolerances to be able to fit so much capacitance in such a small package. And this is also what goes wrong here, because these capacitors work, but if you're unlucky, at some point they just stop working. So because they are so tightly or so so complicated to manufacture, every so slightly error that happens during manufacturing can lead to problems down the line. And this is exactly what happens with a lot of electronics these days, and especially with this USB-C dock, because it's always one of these guys that fails. So, and when they fail, what they do is they become a short circuit, because you can think of them as a million tiny layers of electrolyte stacked on top of each other. And if one of those tiny layers gets damaged, it just connects the two sides, so the positive and negative side together, and then this capacitor becomes a very low impedance short circuit, which of course renders your product completely useless, because then the 20 volts that should go into your product are always shorted. So there is never any power going into your load, it's always shorted. But this, however, does not yet explain why there is damage to the board, because when one of these guys is just shorted, let's say this guy was shorted, then all that would happen is that the charger would detect that there is a short on the output and would shut off right away, and you would still have the short and your product would still be dead, but you wouldn't have any damage, any visible damage at all, at least. What happens now is, because here is a short circuit, each time the charger is plugged in, first, this inrush current limiter tries to turn on and passes current in a certain way until it's just too much current and the charger detects the overcurrent and shuts off again. But then again, 1 second later, the charger tries again, puts out 20 volts again. This inrush current limiter tries again to charge this circuit, limiting the current. And of course, it still doesn't work because there's still a short circuit. So this process happens continuously, repeatedly. So the charger kicks in, the overcurrent limiter does its, the inrush current limiter does its thing, and then the charger shuts off again. And this happens once a second, 2 times a second, continuously. And this circuit is not designed to operate continuously. It's designed to be operated once when you plug the charger in, and then be basically closed switch for the rest of the time. So this circuit is not designed to handle a continuous amount of power put into it. But this is exactly what happens when there's a short circuit. When there's a short circuit, this circuit is used a lot of times repeatedly. So this MOSFET is basically the device that receives all the power. So all the power that the charger outputs until it detects the short circuit doesn't really heat up the capacitor because that's a dead short. It heats up this MOSFET when it's in its linear region, so when it's trying to limit the current. So this MOSFET sees a lot of power over time, and it's just not rated for that. It's not that this MOSFET is bad, it's just not designed to be able to handle a continuous amount of power put into it. And then what happens is one of these guys fails, it's a short circuit, and then whenever or as long as you leave this plugged in, this MOSFET will basically get grilled. It will get power all the time through it. It will heat up and heat up and heat up further and further and further until it finally fails thermally, which might look as catastrophic as it does here. So it melts itself, and it also starts to melt traces and everything around it. And just to give you an example how hot that gets, this is what it looks like after I removed the component and trying to desolder all the leftovers. You can see that still this big pad on the bottom here, this is a part of the MOSFET. And also there are legs still attached here, and you cannot desolder these because when they got so hot that they actually welded themselves to the traces. So there is no way to remove this just by soldering. You would have to heat it up to 1000 degrees or more, which of course is not possible on a board like that. So this MOSFET actually welds itself to the board. So this is what happens. One of the capacitors here fails because they are, in my opinion, over-specced or too small to be really reliable. But Lenovo apparently thought it was a good idea to use them. There are not only 4 of these are just the 4 that are directly visible in this picture or in this area. There are a lot more of these capacitors spread throughout the docking station, and it's always one of the 22 microfarad ones that fail. It doesn't have to be one of those here right on the output of the inrush current limiter. It can be any one of these in the whole unit, but it's always one of the 22 microfarad capacitors that have this relatively small size. So there are 2 things you have to do now. You have to find the one that's actually failed, and you have to replace or bridge the inrush current limiter. So ways to find a shorted capacitor is you can inject power, so you can solder wires to here and here, and just from a power supply or something else you can inject voltage and current into the circuit. Of course, limit the voltage to 20 volts and set the current to whatever you want, because this capacitor is now a dead short. It will conduct as much current as you want. So in my case I went, I think, with 10 amps in the end, and that only took like 2 volts to drive that current. And when you do that, you will see, or you will have to find out which of the capacitors gets hot. So there is a method that Louis Rossmann uses to just pour liquid, in that case alcohol, on the board, and at some spot it will evaporate a lot faster. In this case, if you put alcohol on here, you will see one of these guys evaporating all the alcohol, so basically cooking it. And this way you can see which one is the broken one. Or if you're a little more fancy, you might have a thermal camera at hand, so you can just have a look at the whole board, see which of the capacitors is lighting up on the thermal image, and then you know that's your culprit. So all you really have to do is desolder one of these capacitors that is broken. It's sufficient to just replace one. If you really want to be sure, you can replace multiple or all of them, just to be sure that none of them will fail in the future. When replacing them, you will most likely not find a 22 microfarad 25 volt capacitor that is small enough to fit on here, because as I said, usually with 22 microfarads and 25 volts these tend to be a lot bigger. So what I always do in that case is I scraped away some of the green solder stop paste here and just put a bigger capacitor on there. Just why the hell not? It doesn't change the behavior of the circuit. And also, to be honest, you might not need 4 times 22 microfarads there. The circuit will most likely also work completely fine with 4 times 10 microfarads or even less. So if you're not able to replace it with a 22 microfarad capacitor, that's not the end of the world. If you're just removing one of these 4, for example, you could also just leave it out. However, these are 22 microfarad capacitors and they need to be at least 25 volts. So when you replace them, make sure to put at least a 25 volt rated capacitor there, because it will have 20 volts on it. But if you're not able to find a 22 mic, you can also use a smaller one. So that fixes the short issue. So let's say C8 was shorted, you replace that, and now your short is gone. You can measure that from here to here there is no short anymore. So now that you have replaced the capacitor that was shorted, of course we still have to do something about that inrush current limiter and that exploded MOSFET. So of course the nice thing to do would be to replace that MOSFET with a matching or a proper replacement to keep your inrush current limiting functionality. And for that purpose, this is the data sheet of the MOSFET that they actually use. It's an alpha and omega AON 7403 P-channel MOSFET. The key specs of this, of course, the drain source voltage has to be at least 20 volts. So just to be safe, you should go with a 30 volt unit. And also the drain current, the continuous drain current, for this one is specified with 30 amps. It will never have to conduct 30 amps. This is just good practice to overspec your MOSFETs a lot so that they don't really get hot. So in this case you might end up using, I think, 5, 6 or 7 amps maximum. So this MOSFET can easily conduct that without getting warm, and that's the idea here. So when you replace it, choose one that has at least 30 volts drain source voltage rating and at least, let's say, 25, 30 amps continuous current rating, so that it will also have no problems conducting this current. And then down here you see the exact package that they're using. So this is called a DFN 3x3, so it's a 3x3 millimeter package with this surface mount layout on the bottom. So you have the big drain pad, and then you have 4 little pins, 3 of which are source, and the 4th one is gate. You see the pin out here, and that obviously also matches what we saw in the photo before. So when you want to replace this MOSFET, again, just look for any MOSFET in the DFN 3x3 package that has at least these ratings and an RDS on. If it's able to handle 30 amps, it will have a low enough RDS on, but just make sure that it's in this area also. So let's say below 30 milliohms, that's totally fine, and double check the pin out. Usually in my experiences, all MOSFETs you can get in this package will have this pin out, but just double check to be sure that the gate is actually on this side, and obviously when soldering it on, just make sure that the pin 1 matches up. So let's just for a second return to this picture here, because as I said, there are still parts of the old component on there, which of course is not ideal. So you could try to solder the new component on top of that, but this is usually not going to work out because this is all now welded and not really able to accept solder anymore. So what I ended up doing is I would just cut away the parts that are still stuck on there, bringing the trace with it. So I would cut the trace off around this edge here and also cut off the traces here. So this of course leaves you not with the nicest of pads. However, if you are replacing the MOSFET there, you might end up having to get a little creative anyway. So once I cut these parts of the traces, I just remove some more solder stop mask from here and put fresh solder on here, do the same here, and then just hot air, or if you don't have a hot air, you can also do it with a soldering iron, but if you have this hot air, just do it with hot air, put the MOSFET in there, make sure there is no short between the gate and the source pin, because these are the only pins that are really close to each other, but instead that the gate is only connected to this trace and the source is also only connected to here. And then just double check with the multimeter that there's no short from here to here, or no short from the output to ground or anything before you turn it on for the first time. So this replacing this MOSFET is obviously the nice way to fix it, because then you rebuild the circuit and you end up with a circuit that still has the functionality of an inrush current limiter, so you still prevent those high current spikes in the beginning when you plug the charger in. However, this is not always possible. In a case like this, where most of the traces are just eaten away and the resistors are all gone and the capacitors are all gone, you could rebuild that, but you would have to go through a lot of trouble to get the circuit functioning again in this area now. So what I do in that case, I just remove all the residue and all the leftovers. So I remove the rest of the MOSFET. I remove all this brown stuff because it might have gotten conductive over time. And then all I do is I run a jumper wire from here to here. So I basically bridge the incoming power straight to the output of this inrush current limiter, using a wire that is thick enough. So it doesn't have to be crazy thick, but it should also have a sufficient diameter to conduct 7 amps. So make of that what you will. 1.5 square millimeters is maybe a little bit too big, but just something that works in there. And when you do that, so when you run a jumper wire just from here to here, you have basically also made the device work again. You will just no longer have an inrush current limiter. So just don't plug in and out your USB-C dock 1,000 times a day, because this will create wear on your connector. Just think of that you no longer have an inrush current limiter. Make of that what you will, but your device will still work fine even without the inrush current limiter. And since this video is more or less about how to get this USB-C dock working again, because it's, in my opinion, quite an expensive thing, and it fails a lot too often to just be thrown out every time. So what I would suggest is try if you can get the functionality of the inrush current limiter restored by replacing this MOSFET entirely. And if you're not able to, just run a big jumper from here to here, have no inrush current limiter anymore, but still have a working USB-C dock again. Yeah, that was it about this. As I said, I had this issue 4 times now, so I had 4 of these USB-C docks on my desk, and they all had exactly the same issue. So they had one of these 22 microfarad capacitors fail, and subsequently this inrush current limiter MOSFET burn itself out, and all I had to do was either replace it or jumper it, and then the unit was completely working again. There's also no reason to believe that there is another issue now, because as soon as one of those 22 microfarad capacitors fail, they basically short the 20 volt that's incoming to the dock straight away. So there is no power going anywhere else but to that short. So it's not like any of the ICs got an overvoltage or the circuit was in some unstable state. It was simply the 20 volts that were supposed to go into the device were shorted. That's it. So as soon as you remove that short and you make this inrush current limiter work again, your docking station should be fully working. There's no reason to believe that anything else is wrong. Okay, so this video turned out to be a lot longer than I had anticipated, but that's all the information I have on that topic. And if you are in the position that you have one of those docks in your hand that simply refuses to turn on and you didn't know why and you didn't know what to do with it, I hope this video gave you the information to answer these 2 questions, even if your consequence is now to throw it away because you don't want to go through the hassle of repairing this. But maybe you are willing to repair this, and then I wish you the best of luck. That was it for today. See you in the next video. Bye.